The next topic of discussion here is IP multicast routers, how they forward multicast traffic, and how they learn the appropriate routing information in order to forward these packets. Now it's true, a vast majority of multicast routers also perform unicast routing duties. But the mechanisms and the logic they use to forward unicast packets versus multicast packets, it's vastly different. And it is a good use of an engineer's time who is trying to learn multicast the first time up to understand these differences, to realize visually how all of this is being put together and how they are actually different. So how can you leverage some of your unicast knowledge into multicast and the new things that you need to learn in this particular realm? So the forwarding basics. It bears repeating the actual comparison to unicast packet forwarding. In unicast packet forwarding, we have always been taught, and really the routers behave in such a way, that the packets always are guided towards a destination. So each packet has a destination IP imprinted on it, and that destination IP is basically looked up at every hop on every single router, and it is guided further towards that destination. So really the only source of interest in a unicast packet is the destination IP contained therein, and then the router essentially guides the packet further and further towards the source. In multicast packet forwarding, this basic mechanism has changed. The multicast routing packets, or the multicast packets, are really, in a sense, guided away from a source. So you're not necessarily guiding them towards a particular recipient or a receiver or a destination. You're really trying to take them safely further and further away from their originating source. And we'll learn why this little distinction is very, very important in the rest of this lecture and really the rest of the course as well. But really, every time you think of a multicast packet being quote-unquote routed through a network or forwarded through a network, think of it as being forwarded away from a source versus towards a destination. So that brings us to the interface types for multicast sources in this sense. So when you look at a unicast routing table, it's always organized by destination IP addresses. There is always a next hop IP that is associated with those routes. And furthermore, if you look at the actual forwarding table, there's always an exit interface. So that would be the interface where you would put a packet with that destination on to take it further towards that destination. In multicast, you need more than one type of interfaces. So the routing table really has to keep track of multiple types of interfaces. The most important one here is the upstream interface. Now this interface is metrically closest to the source. And those of you who are thinking that this sounds like the exit interface of the unicast routing table, you're actually correct. It is literally the exit interface. If that source was a destination and you were looking for it in the unicast routing table, yes, that interface would actually be the exit interface, metrically closest to the source. Now note the use in those two bullets, upstream and downstream, note the use of singular and plural. So the singular is used here because out of all of the available ECMP routes or ECMP interfaces, multicast routing table for a certain multicast route will only pick one. So it'll hash out the contents of whatever packets you're needing to forward, and you would pick one. So one upstream interface per multicast source and really multicast group. And this happens to be the metrically closest source. Now, in addition to this, once you receive the packet on an upstream interface, you really need to forward it somewhere. So guiding away from a source is fine and dandy, but you really ultimately need to get it to your receivers. For that, there are always downstream interfaces. Now, these are all of the interfaces that have two qualifications. They are not upstream interfaces, so you're not sending the packet back towards the source. And they are really interfaces where they have been interested receivers. So some receivers who are interested in receiving those groups, they have already identified these interfaces, or they have used multicast routing protocol to signal their interest in these particular groups. And once that signaling comes in from those downstream interfaces, or those interfaces, they then become the downstream interfaces for that source and that group. Now, this entire concept has an overarching term that is used, and this is called the reverse path forwarding. Because what are you doing? You're trying to forward the packets, the multicast packets, on a path that is the reverse path from the source. So if the source was the destination, then you would take a certain path to go to it. And you are really trying to use the same path to take the packets away from the source. So reverse path forwarding is the overarching term that encompasses all of these little intricacies of multicast routing. So multicast routers, they have a multicast routing table. Just like unicast, they would have a multicast routing table of their own. And that routing table has what are called quote-unquote multicast routes. That's not the technical term, but that's the term you would see most often being used. And you would see things called S, G and star, G. If this doesn't gel together just yet, believe me, we'll be talking about these terms so many times over the coming lectures that they would really become second nature by the time you're done with this. So let's look at the multicast routing table. First of all, we have to find what sort of information is being stored inside that multicast routing table. So really, a multicast routing table, somewhat like a unicast routing table, stores and organizes information in some fashion. In this particular case, the organization of the multicast routing table is by the groups. These are the actual multicast groups. So think back to lecture 1. And these would be all of the class D addresses between 224/8 to 239, 255, 255, 255. So all of those groups, every individual one, will be stored in the multicast routing table, and there would be some information that is associated with it. Now, to be absolutely technically correct, those are not called routes. They're really called forwarding states. So whatever information you see inside a multicast routing table, those are actually forwarding states. So here is a small, on the right side of the slide, there is a very short, succinct capture from a actual working routing table. So first of all, the command itself, this is from a Cisco iOS router, but other vendors would have something similar in there. But show IPM route. So I need to see the IPM route information, and I am looking for a certain group. So in this case, I'm looking for something in that administratively scoped block, 239.10.10.10. So there is a group 239.10.10.10. and I need to see information regarding that group. So already you can see here's a star, G, then there is an S, G, but we need to understand what all of this is. What this really is that every single multicast group, so every single stream or every single bunch of packets, the packets have to originate somewhere, and that somewhere is the source. So all of those packets start at a particular source, and that becomes then the S in multicast parlance. If the group is G, then the source is S. Now with multicast, it's a little bit more detailed than this. So there may be specific sources where you actually know about the IP of the source, or the source has sent multicast packets and you've captured them, or a receiver has indicated that there is some source that it's aware of via configuration or whatever. But there is a known source. That's the final thing. There's a source and you know its IP. In that case, the source is simply called S. And the corresponding entry would look something like this. So if you looked at the multicast routing table, the corresponding entry would have a defined IP. This is the S. and a defined group. This is the G. And ultimately, this becomes the S, G entry, as opposed to an unknown source, or really any source at all. So sometimes the receiver may say that I am interested in every source that is sending to this particular group. It could be that, or that you do not know of the group yet. So it's either any or it's unknown. Either way, we use a star or an asterisk, really, to identify a wildcard source. So plug in anything in here as long as the group is good. That's what I'm interested in. And that manifests itself in the routing table as really a star. So it's a star and then a comma G. So star, comma G. So now, because there is this understanding about the sources, known sources versus unknown sources, I can further organize that table, or the router can further organize that table by a combination of sources for the groups. So each group will have a source, or will have any source, star, comma G. So you'll create different forwarding states depending on the known or the unknown source. If the source is known, then you create an S, G forwarding state. And that S, G forwarding state is right here. So there is a known source, 172.26.1.0 in this case, and there is a known group, 239.10.10.10. Now the group is always known because that's how you organize the table. But in this case, this is the S, G. As opposed to when you do not know about the group, when you do not know about the source. So in this case, you will replace that S with a star. So it's a star, G, and it is literally telling you that it is either any group, or it's either any source or an unknown source. And that manifests itself in the table as literally a star, G. So this is that star, G entry. So star, G for unknown or any source. Again, if this is not gelling just yet, just remember, if you look at a multicast route, you're going to see some sort of S, G. Either it's going to be a star, G or a defined IP, but you should expect to see for every group more than one or two of these types of entries. This is how the multicast routing table is really organized. Now, more information. So we've already talked about what particular route or what particular forwarding state am I collecting information for. So that information really is residing here. So this is the entry, or these are the forwarding states or the routes I'm collecting more information for. In Unicast, that information would be the attributes, would be the next hop, would be the metric, would be the exit interface. In this case, in multicast, for the very, very basics, so for the very, very basics, I need to know the associated set of upstream interfaces. So what upstream interfaces relate to those entries, the S, G, and the downstream interfaces. Because that's what I need to see, because that's where the packets are going to come from, and that's where the packets are going to be forwarded to. Like I mentioned before, there has to be a single incoming interface. So once again, if you're looking at ECMP, or if those thoughts are going in your head, the multicast routing table will identify via hashing or some sort of algorithm a single upstream interface. That's not an option. It's always a single upstream interface for a combination of a source and a group, or an S, G. In multicast parlance, again, this is called the IIF, or the incoming interface. So IIF, or the incoming interface. Let's look to the right and see if we can find these interfaces, right? So in this case, here's an incoming interface for the star, G, happens to be fast Ethernet 01. And there's an incoming interface for the S, G, which happens to be fast Ethernet 00. So again, don't worry about how these interfaces were chosen just yet and why they are really different for the same group. But just know for right now that you should be expecting to see this. And really, the packets that are coming down those multicast streams really have to arrive on these interfaces, or there are problems, right? We'll get into that. The second thing here is the outgoing interface list. So packets have come in already. Now you need to forward them towards some destination or some set of receivers. This is always contained in an outgoing interface list. So because you need to be ready for the possibility of having multiple receivers, this really needs to be a more modular structure than a single incoming interface. So this is always a list. And it's called the OIL, right? So outgoing interface list, or the OIL. Now, this list itself, just because it's a list, doesn't mean that there is that we are suggesting that there are multiple receivers always. For example, if you look on the right-hand side again, it can have actually 0 interfaces. So this is a list of 0 interfaces. And that's completely legible. This was taken from a production router. So this is completely legitimate. On the other hand, out here, it is a list of 1 interface. There could be other scenarios where it could be a list of greater than 1 interfaces. So that really just depends on how many receivers, how is your network actually designed. But know for right now that OIL is very important. You have to have some interfaces in the OIL for the multicast forwarding state to actually work. But that really puts it all together. There is a forwarding state. That forwarding state has an IIF and it has an OIL. And as long as those things are working properly, multicast works properly. So creating these correct forwarding states with all of the listed components, the 3 things that I've repeated, that really then becomes the task of a multicast routing protocol. So we will be talking about this, but multicast routing protocol, it is to actually populate this table. All of this information really is coming from the multicast routing protocol. Again, it bears repeating that for every single source, group combination, a single route will be chosen. And that's why there is always a single IIF. And this is not up for debate. There's always a single IIF. Now, as new receivers join or leave, the OIL can be updated or downgraded, so it may have 0, it may have 1, it may have greater than 1. So OIL is ever changing, but the IIF, well defined in a stable network. We have talked about what is contained in the actual multicast routing table or the forwarding table. So now it's time to talk about how that table actually gets populated, hence the multicast routing protocol. The multicast routing protocol in a domain has 3 primary responsibilities. It does other things too, but for every single forwarding state or every single what we have called route, it has 3 primary responsibilities. Those responsibilities are, first of all, identify an upstream interface, or the IIF. That IIF identification is actually one of the most prominent responsibilities or the most important responsibilities of a multicast routing protocol. So identify the upstream interface. For the most part, by default, it'll just use the unicast forwarding table. So remember we talked about the exit interface? It's literally going to pick one of those exit interfaces. So this is by default. Now this particular interface is going to be on the shortest path towards the source, right? So it then becomes the upstream interface. For a network that is more customized, where maybe unicast doesn't really jive with multicast and they have different information, it is important to understand that this can be overridden, or this information for the IIF that I'm using can be overridden with multicast specific information, but that's topic for a later lecture. Right now, just know that we are not we're not handcuffed with the unicast forwarding table. We can make our own decisions. But that's really fine-tuning multicast. By default, it's just going to use the unicast forwarding table. The second important responsibility of the multicast routing protocol is to identify the downstream interfaces, right? And these are contained in the OIL. So once again, I'm going to emphasize that it is not just an exit interface, it's actually an outgoing interface list. It's a list of interfaces. The routing protocol will have the fine-tuned procedures that will allow the receivers to signal their interest. Because how else are you going to create this list? Because remember, the outgoing interface list is the set of interfaces where there are active receivers for that forwarding state or for that multicast stream. So it is very important that there are some procedures built into the multicast routing protocols for the receivers to signal their interest in that particular group. Now, as the requests come into the router, the OIL is created. As they sort of leave, the OIL, it is completely dynamic. Which brings me to the very third point here. You have to maintain dynamic multicast trees. And we'll talk about multicast trees in a couple of minutes here. But for right now, remember, all of this happening in a multicast network, it's completely dynamic. Sources may come online, sources may go offline. Receivers may come online, receivers may lose their interest in a particular group and ask to be removed. All of this is happening extremely dynamically, and it is the task of the multicast routing protocol to take care of all of that. So it has to change the forwarding state as and when these things happen. What are the actual procedures? Again, we will talk about them in much, much more detail. But for right now, if we remember these three primary responsibilities, we can really start wrapping our head around what multicast routing protocols actually do. Finally, we have the multicast routing protocol working. It has taken all of this good information, it has provided that to the router has created the forwarding state. Finally, the packets start arriving. So how does the data flow actually work? So multicast packets, they should always arrive at a router, or the router expects them to arrive in a certain fashion. And that certain fashion is the IIF. So they must always arrive on the IIF. Once they do arrive on the IIF, they will be forwarded by the router, and they would be forwarded to, you guessed it, it should be on the OIL. So they should be forwarded on the outgoing interface list for the particular group. Keeping this consistency, making sure that they're arriving on the right upstream interface or the incoming interface, and they are leaving on the proper downstream interfaces, that is critically important for multicast to function properly. If one of these things break, for all intents and purposes, multicast breaks. Furthermore, if these rules are not really followed, it leads to the formation of loops. Yes, that dreaded topic called loops. But multicast loops are actually more dangerous than unicast loops. So in unicast loops, the same packet may be sent over and over and over again back and forth between a couple of routers. The dangerous aspect of multicast is really due to packet replication. So at every hop, we may be replicating that packet. We may be making multiple copies of that packet and introducing those packets into the loop. So ultimately, it leads to multicast storms. So it cannot be emphasized enough the importance of stopping the formation of these loops. And we'll be talking about that in much more detail. So here is a look at the actual multicast tree. So multicast forwarding states, when you're looking at them across different routers, they really are called multicast trees. Because once a forwarding state is created, so every router between a source and a receiver, so in this particular case, we should have had receivers down here. So suppose there are receivers here, maybe here, and maybe here, and this is the source up here. Once the forwarding states have been applied on all of these routers, so all of these mid-hop routers or whatever routers are lying between the source and the destination, so you create a state here and a state here, there, and all of these routers, all of those states will have an IIF, so that's where the packet flows in from, and they will have an OIL. So packets coming in via the IIF and leaving out via the OIL. Once you start putting these things on paper and actually start building out the topology, you will find that it usually results in this nice little tree structure. Now, it could be a tree with a single stem and a single branch, but ultimately in a busy network, you should have multiple interfaces in your OIL, and it should look like an upside down tree. Where there is a tree, there are branches, but more importantly, there is the root. Right now, we'll talk about one type of root, and that would be if the source is actually known. We'll leave the other part for the star comma G off discussion for right now. But if you look at it, all of the packets on this particular tree that I have drawn here, all of those packets really originate at this source, because this is the tree for this particular S comma G. So the packets always have to originate at the source. And once they originate at the source, they travel down this tree and forward and away from the source right down to the receivers. So this then becomes the root of the tree. So what have we learned here? We have learned here that for shortest path trees with known sources, so really S comma G trees, they are rooted at the source itself. And they're also called the shortest path tree because if you're following all of the information about the IIF and you have IIFs here and you have OILs here, so let's see all of the IIFs in green. So this is the closest interface facing the source at router 1. This would be at router 2. The next routers would have some IIFs, and these routers should have some IIFs. So if you look at it, the tree only has the shortest path from the receiver to the source. So hence it's called the shortest path tree. The star comma G with the unknown source or any source, it's actually called a shared tree. Why? We'll give you more information later, but right now it's too early in the concepts to go into star comma G trees, so we'll table that issue for a later time. But right now, know that S comma Gs, it's very easy to see, they are rooted at the source. So there is a tree, there is a root. For S comma G, that just happens to be at the source itself. No discussion about multicast would be really complete without talking about the looping aspect of it. We have touched this in a previous slide, but here is the time to actually visualize how this loop would actually blast into a full-blown storm. So here is a simple topology, and suppose there is no multicast routing protocol working on it, right? So we are just treating multicast, for example, like broadcast. We let it come in through an interface and we bombard it out of all of the exit interfaces that we have. Let's follow the journey of a single packet, a single multicast packet that comes from that source. It arrives at R1 and R1 creates 2 copies of it. It sends one to R3, it sends another one to R2, or it sends another one to R2. How about that? So now they are separate copies. R3 receives it on an interface, and because it's multicast, it should forward it out of the other interface. So it sends it down to R2. R2 receives this blue copy and sends it over to R3. Now I think you can already visualize what's going to happen here because R3 is not really checking anything in these packets. There is no multicast routing protocol. It'll receive this blue stream or the blue packet and it will forward it down to R1. R2 would do the same thing to the green packet, forward it down to R1. Now R1 received a single copy of that packet, but ended up receiving 2 copies back. Not only that, it is going to now, if it's not again following any multicast rules at all, it'll send both of those copies back to the receiver. Not only that, the green copy now is forwarded again over to R3. The blue copy is forwarded again to R2, over on this side, over on that side. So ultimately you can see that this is turning into a full-fledged storm. And that's why stopping this looping is one of the most important tasks of a multicast routing protocol. Now, ultimately, this is not as bad as it's marginally better than a layer 2 looping storm because there is no TTL there and there is IPTTL in it's IP multicast, so there is some TTL concept here. But that would be literally the very last saving grace, and the packets would have looped several times before this TTL actually expires. Like we said, one of the major tasks of a multicast routing protocol or the forwarding plane is for the loop prevention. For the vast majority of multicast, this loop prevention manifests itself in something called the RPF check. We have already discussed the whole concept of RPF and how we are trying to forward packets away from the source. And this was the whole concept of the IIF and the OIL. So the multicast loop prevention really is carried out in the data plane. What the router does is it inspects every single packet that arrives, multicast packet that arrives at the router, and it makes sure that it is going through the reverse path forwarding check. So the reverse path forwarding check is actually the RPF check, is performed on every single router. The logic is very simple. Actually, the name may be freaky, but the logic is very simple. The multicast packet arrives, and the router inspects the source IP. So again, like I said, source is very, very important in multicast forwarding. In this, the router is inspecting the source IP. It's not really concerned with the destination or the multicast IP yet. It's only worried about the source IP. The source IP for that group, so S, G, must have an IIF. Remember, the routing protocol already did this job for us. It has identified an IIF. It has identified an OIL. So the router looks up this IIF, and if the packet was not received on that valid IIF, that one IIF, it is literally dropped. You will not be forwarding that packet anymore, and you will be killing the loop preemptively. By default, because of the way the multicast routing protocol works, the multicast routing table uses the unicast forwarding information base. We have discussed this before. And as we have discussed before, it's very easy to override this with specific information. Now let's take a look at the earlier scenario, this time with the multicast RPF check stopping those multicast loops. As we discussed, the stream of the packets, the multicast packets, is going to come in from the source, 192.168.1.100. But this time, pay attention to the actual routes that are being utilized here. On R1, you have a directly connected interface. So let's identify all of the IIFs, or incoming interfaces, with this green marker here. So on R1, there's a directly connected route. Hence, that particular interface with the directly connected route becomes the IIF. Moving on to R2. On R2, there is a specific route for that /24. Assuming that is the most specific route, then wherever that route points, whatever becomes that exit interface, then that becomes the IIF. In this case, that exit interface should be connecting to R3 because that route is via R3. So this interface between R2 and R3 now becomes the IIF. Moving on to R3, there is a similar route, but this time it points towards R1. So the R1, R2, and R1, R3 interface now also becomes the IIF. Thinking back to the RPF check as we discussed it, if the packet does not arrive on the IIF, it will simply be dropped. So on R1, as it did before, it creates 2 copies of this packet. Now this packet, the blue packet from 192.168.1.100 has been received on the IIF. There is a green marker there. So R1 will create multiple copies of this, forward one to R2, forward another one to R3. So let's say the green copy was forwarded to R2 and the red copy was forwarded to R3. Now R2, once it gets that green copy, will realize that this is not the copy has not been received on the IIF, because the IIF does not belong between R1 and R2. That means this packet is actually just stopped in its tracks and it is dropped. That packet never actually makes it anywhere because it was not received on the proper IIF, so it failed the RPF check. And because of the failure of the RPF check, that packet was dropped. On R3, however, the red packet did arrive on the IIF interface. So it can now be safely forwarded out to R2. R2 receives the same packet also on the IIF. So that is now consistent. This particular packet will also pass the RPF check and actually really would be forwarded anywhere it needed to be forwarded without causing a multicast loop. So with this simple data plane trick, or data plane check if you will, the RPF check, multicast loops can literally be stopped before they actually form. Finally, we have to talk about the RPF check override. As I discussed before, there can be cases where the multicast topology does not really match the utilized topology. In this case, the RPF check, if they utilize the unicast routing table, they will obviously cause problems because the exit interface is not really the expected IIF, and ultimately the packets will be dropped. Some of them may make it through, some of them may get dropped later on. So because of this, most of the vendor implementations allow for simple RPF overrides. And essentially you build a separate routing table for the RPF checks. Really what is happening is that forwarding state that we talked about every source comma group, S comma G, that information, the IIF information in there, is not being pulled from the unicast routing table anymore. It is being pulled from some other means. Some of the different ways is you can run multi-topology IGP implementations. So you run one set of IGP database for unicast, and another set of IGP database with separate metrics, separate routes, separate neighbors for multicast database. MBGP can be used. So multi-protocol BGP, the multicast implementation of it can be used, and all you are really exchanging the NLRIs for is for the explicit use of the RPF check. And finally, the easiest one is the so-called static multicast route. Now it is called the static multicast route, I'm assuming, because of the actual command on the Cisco routers. So the actual command on the Cisco routers is IPM route, which makes you think of the IP route command, which actually does set a static unicast route. But ultimately, IPM route is really just an RPF override. And that point is proven by what goes in this network and the mask. The network and the mask here are not multicast addresses, because that would really not make sense. This is not a multicast route. These are actually unicast IPs. Again, we'll be discussing these in much more detail, but ultimately what you're trying to say is, for a particular source, stop relying on the unicast routing table and instead use another next hop which should lead to a different IIF and should really make the implementation more consistent with what the multicast topology actually looks like. That brings us to the end of this particular lecture, and I hope you've enjoyed it.